Okay, so thank you very much. And first, I would like to thank the organizers for the invitation. And indeed, I will talk about recent work we did with Joachim Bernier concerning the smoothing properties of semigroups generated by accretive quadratic operators. And the class of operators we are interested in is the following. Given Q a quadratic form taking complex value defined on the phase space and with a real non-negative, real part, we consider the associated accretive quadratic operator, which is simply defined by the Weil quantization of this simple Q. And we consider this operator equipped with this domain. And since the Weil quantization of a monomule of degree 2 is simply this differential operator, we're just considering a class of non-self-adjoint differential operator. And we are interested in studying the smoothing properties of the associated semigroup. That is, we aim at understanding how the non-commutation phenomena between the self-adjoint and the skew self-adjoint parts of the operator Q-Weil, that is the non-commutation between the real part and the imaginary part of the quadratic form Q, allow the associated evolution operators to enjoy some smoothing properties in specific directions of the phase space we aim at sharply describing. And more precisely, we want to find the vector subspaces of the phase space containing the smoothing directions for these operators. That is, given m vectors in this vector space, x1, xm, we want to differentiate our evolution operators in the directions given by x1, xm, and keep a linear bounded operator on L2. And by differentiated in a direction given by a vector x0 of the phase space, I just mean applying this differential operator with this operator. It's just the canonical Euclidean scalar product on R2n. And another objective is to understand the behavior of the norm of these operators with respect to the time variable t and to the integer m, that is to the number of differentiations we are applying. So this is a general problematic for semigroups, and to perform this study for the ones generated by accretive quadratic operators, we have to introduce a central object in this theory, which is called the singular space, a vector subspace of the phase space, introduced by Michael Ittrich and Karel Pravda-Starov. So this is this intersection of kernels where the matrix appearing there is called the Hamilton map of the quadratic form Q, which is simply its representation through the canonical symplectic form of R2n. So this vector space has been shown to play a key role in the study of Q-Weil or the semigroups generated by this class of operators. And what we've proved with Joachim Bernier is that the orthogonal of this vector space contains the smoothing directions for the associated evolution operators, so the smoothing directions as I defined in the previous slide. And we could also characterize the behavior, the short-time behavior of these smoothing properties, when there the behavior in small times is characterized by indexes, which are called integers, which are called indexes of the directions we are differentiated our operators. This is a notion also introduced by Ittrich and Pravda-Starov. I won't define precisely there, but is defined is linked, to the structure of this orthogonal complement. And we also have their behavior in factorial or in square root of factorial m. That is, these operators enjoy partial, let's say partial Gelfand-Shiloff smoothing properties. I won't go into the details of this proof, but I would like to present the main approach of this proof. And this is based on another result we obtained with Joachim Bernier, which consists in describing the polar decomposition of the evolution operators we are studying. More precisely, we can obtain the existence of a family of non-negative quadratic forms and also a family of metaplectic operators, such that our evolution operators can be split as the sum of a self-adjoint operator and a unitary metaplectic operator. The self-adjoint part being defined in the following way. Moreover, we have a precise knowledge of these quadratic forms A of t in short time, since we can obtain the following Lauer bond. And we can notice that the single space I've introduced is the isotropic cone of the quadratic form appearing there. And we can also sharpen this polar decomposition by proving that the unitary part also has a semi-group interpretation, that is, can be defined in the following way as the self-adjoint part there. So with this decomposition result, the study of the smoothing properties of these operators can be reduced to the study of the ones of these self-adjoint operators, since we can forget the unitary part. And so we can just work with the family of self-adjoint operators which are quite well known in short times. And so we can perform the above study and prove the first theorem I've presented. And this polar decomposition result can be proved by using the Fourier integral operator structure of these evolution operators, which was described in a paper by Lars Ormander from 1994. Okay, so just a remark to say that the very same study can be performed for semigroups generated by another class of operators, which are non-self-adjoint and also non-local operators, the fractional Ornstein-Beck operators defined as the sum of a fractional diffusion and a linear transport operator. And the two applications of this study are the following. First, we can study the subelliptic estimates enjoyed by the operator Q-Weil, and we can also tackle null controllability issues for the evolution equation associated with this class of operators posed on the whole space. And I refer to the presentation of Karel Pravdastarov for new controllability results. And I would like to finish with some references, and I thank you very much for your attention.
Thank you very much for this interesting talk. Are there any questions?
Yes, if I may.
Yes, please.
Also, if you go back to the slide where you have this decay properties.
Yeah.
Because then, yeah, that's right. So there you have something which is optimal then. So
yeah, this is okay. We didn't prove that this is optimal, but we believe that the short time behavior is optimal indeed.
Mm-hmm.
And the reason for that is this inequality on the self-adjoint part of the polar decomposition, since we also have the other inequality there, okay, the lower bound. We didn't prove that, we didn't write that, but we convinced ourselves with Joachim Bernier that the other inequality is also true, and therefore this behavior in short time, just like I said, seems to be optimal. Yeah. Mm-hmm. And so is behavior the square root of factorial m. That we are sure that this is optimal, since in the case where S is reduced to 0, the orthogonal, of course, is R to N, is the whole space, and therefore these operators enjoy, let's say, a complete Gelfand-Shilov smoothing properties, half-half, and this is, of course, we know that this is optimal from the Heisenberg principle.
That's right. Thank you.
Thank you very much. Are there any other questions? If not, I would like to thank our speaker on behalf of all of us. Thank you very much, Paul.
Thank you.
And